Okay, so let's move on. Let's talk about superposition. So superposition is the ability of a quantum system to exist in multiple states simultaneously, in contrast to classical computer systems, which can only be in one state at a time. Now we're talking right now at the bit slash qubit or the transistor slash particle level when we're talking about states. The superposition enables quantum computers to perform certain computations much faster than classical computers. By encoding information into the superposition states of qubits, quantum algorithms can efficiently solve certain problems that are difficult for classical computers to solve, such as factoring large numbers. Classical computers just don't have enough horsepower. Now, there's quite a bit of debate about how to describe a superposition in detail. We all get that it is generally a depiction of a spectrum of variance between two or more states, because superposition includes both states or all states. A better way to think about it is as a probability distribution of a point on that spectrum. Now, if you study any math or statistics or AI, you know all about probability distributions, so this should make sense. These distributions form dimensional shortcuts to perceptions. And that shortcut is a superposition or a dimensional representation of multiple states of existence. Now we know they're there because of the slit experiment, so we've proven that already, that they already exist. The state of superposition is a dimensional shortcut to help us humans work with a notion that we do not know the state of something until we measure it. But we can make a really good guess at what it will be with some degree of probability. And that we can work with to do calculations as long as it is consistent representation. This is dimensional cognition at work. Intuitively, we know particles are in one state or another, or some interim state on the spectrum. It doesn't matter whether we believe a particle is actually in two states at once. We can still use the notion of this, both at the same time state, for processing using a wave function. And that's the key. Now, in the prior algorithms, Monsieur Adamar developed a gate that was used to instigate a superposition in a qubit, i.e. its underlying particles. We measure that state and rerun it numerous times to get a probability distribution of state outcomes. And then we can change this distribution physically using particle instigation such that the distribution changes. We alter the probability amplitudes. Now further, a quantum computer can process these potential states simultaneously, limited only by the number of qubits applied to the problem. We can alter the superposition state probability amplitudes. If you think about those waves we saw before, it should make sense that if I alter the wave machine, i.e. the particle, it will alter the behavior and measurement of those waves. You should be able to see that if I loaded data into a superposition state, that changing the state would alter the data in some way as per the quantum gate in the algorithm. This is why quantum data engineering is such a critical component of quantum computers. So let's jump over to entanglement. Entanglement is when two or more quantum particles, qubits, become joined and correlated in such a way that the state of any one particle is fixed and dependent on the state of the other entangled particle on measurement. If I entangle two particles and separate them, then look at the state of one particle at wave collapse, it instantly tells me the state of the entangled particle. This can be the same or converse or spin up, spin down, or both down. You can if you set the state on one particle, it'll automatically be represented in the other particle, even if they're at a distance. This was Einstein's spooky action at a distance. Quantum computers use entanglement to process faster than classic computers, as they can process multiple states of entangled qubits simultaneously. They can set entanglement using the same mechanisms we've already discussed, such as specialized gates, and once an entangled particle's state is measured, then all entangled states are instantly rendered into a dependent entangled base state, i.e., once you measure one, the others collapse into an entangled base state. The way this is done in a quantum computer is to prepare qubits using a series of gates, then apply a special gate to entangle the qubits. You can do this for multiple qubits using a series of gates. So if you think about this, if you apply data into entangled qubits and then impact the states and measure the results, you will see the output you seek if the data is well formed. Quantum computers use superposition and quantum parallelism and entanglement to process data simultaneously at very great speeds, much greater than classic computers. This requires excellent quantum data formation, excellent algorithms, deep understanding of quantum physics and quantum control mechanisms, and an understanding of not just the entire system, but also the real world and how to blend those two together. Abstraction, let's talk a little bit about abstraction, because we use this abstraction in neural nets. Obviously, we abstract data into representations that the neural nets can understand. Well, we also use it in quantum computers. Abstraction of the real world inside the world of a quantum computer is not really much different than how we use abstractions and representations in neural nets in AI deep learning. In fact, we have used representation since the dawn of computers because computers only speak numbers. I cannot emphasize enough how important data representation and abstraction is to encoding data for use by a quantum computer and an AI and deep learning systems. It is critical. We use abstraction in AI in neural networks for deep learning, and the same thing is required in quantum computers. You can't just feed raw data, push some buttons, and get the output you seek. Real-world data needs to be represented in a way that the quantum computer can comprehend it, and in a way that the output of the system can be comprehended by us to solve a problem. In this way, it is similar to neural nets. The task is not easy because it requires deep quantum computer experience and deep real-world experience in the domain for which the solution is sought. It's very hard to find this level of talent at this time. There is also a very large gap between what these systems can do and the real world. So what the heck can we use these quantum computers for? That's the big multi-billion-dollar, trillion-dollar question. Surprisingly, not much right now, but that will change. Currently, they are used to process data that takes an incredible amount of time and resources to compute, but that has an immense value. Areas like cryptography, finance, scientific calculations, and research, that's where these things actually can make money today. Anything where the volume of calculation is exceptionally large. Cryptography, or the factoring of large numbers, optimization problems, etc., etc., etc. Quantum computers hold great promise for the future, especially in advanced AI. The connection to advanced AI is in cognitive AI. The use of quantum computers in cognitive AI is the real takeaway. Because right now we're currently in what would be called, deep learning AI, and this is with chat GPT, chat AI, image AI, rendering, and generative systems. But where the quantum computers provide hope is when we move to deeper understanding of the context, something more akin to what we humans do. like the kind of context we're using now, and the layers and the cascades of context in our response to stimuli. And this is where quantum computers hold their greatest value for artificial intelligence in the cognitive artificial intelligence area. So obviously finance and banking is important, where the volume of information is massive and speed is essential and the value proposition clear. Now in medicine, it's the complexity is related to the mass volume. Now in medicine, where the complexity is related to the mass volume of relatively simplistic interactions, such as protein folds, the quantum computers can add the speed necessary, because the massive number of permutations and combinations of folds is what the issue is. So, and this is the way in a lot of medical and scientific research. It's just there's so much data to process because there's so many optional pathways in the data that the data can go. So we need either massive computers to get the job done, or quantum computers which can process simultaneously. Now, I personally believe the greatest benefit will come in advanced AI, that's cognitive AI, as we move from today's simple but fascinating text and image generative models and into complex, deep contextual relationships, not just in words, but in multimodal perception across various stimuli, so computer vision, sound, etc., etc. Not just artificial general intelligence, but comprehensive machine perception and cognition, or superintelligence. Quantum computers are a piece of this puzzle only. They're not a replacement for the tech, but they are a missing ingredient on the path to superintelligence. Now, obviously, we need to discuss threats. All systems bring with them good and bad elements, and more importantly, consequences. The use of Shor's algorithm to factor large numbers and a quantum computer renders almost all encryption software obsolete. And this can be done now. Bank accounts, secure data, military systems, financial systems, etc., 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 are all at risk now. They're all open to vulnerability if something is not done. Ironically, the solution is quantum computers. New, more complex encryption and cryptography requiring even more powerful systems is the solution, and maybe even going to advanced cognitive superintelligence, which would add another dimensional layer. Lots of other threats than just the obvious, such as manipulation, creation of dangerous weapons, including bioweapons or viruses or even dimensional weapons, negative optimization or undermining bad decisions or negative outcomes of poorly executed systems. That's a threat to us as well, such as the removal of human rights or support for tyranny. Bias and human design flaws are a threat. These are all the same as for AI. Quantum computers could suffer accidents due to their fragility if quantum computers are used as control systems. And again, the computers themselves are not dangerous, but if they're used as a control system on, say, a network of rail cars or something like that, it could be disastrous. So there's lots to consider because these systems are very fragile right now. So this is where we'll end the first part of the presentation. This afternoon we'll move into the second part, which is a deep dive into investing in quantum tech, the infrastructure, the technology, the computers, and even a little bit about AI. Before that, we'll do a lab to build and implement a quantum computer simulator. So we'll do some code and we'll actually make it run, and we'll affect it and change it and see what the results are. And then we'll do a quantum computer sort of / quantum mechanics Q&A, and we have some guests from the quantum computer world to answer your questions who are far more knowledgeable than I am. So they will answer your questions in deep detail, and then we'll go into the afternoon session.